Imagine standing in a quiet control room late at night. The lights are dim, the monitors glow softly, and somewhere beyond everything you can see, a tiny signal is making its impossible journey back to Earth. It has been traveling for nearly 23 hours at the speed of light, crossing more than 15 billion miles of empty space before finally reaching a radio dish waiting patiently on our planet. That signal comes from Voyager 1. At this very moment, the spacecraft is racing through the darkness between the stars. It carries human voices, human music, photographs of our world, and the coordinates of our home. Yet, despite everything it represents, Voyager 1 is slowly dying. Not with an explosion or a dramatic final message, but quietly, 4 watts at a time. One scientific instrument falls silent, then another, like someone walking through an empty house at night, switching off each light before locking the door forever. This is not simply the story of a spacecraft running out of power. It is the story of humanity reaching farther into the unknown than ever before, only to discover that even our greatest achievements cannot escape time forever. And before we continue this incredible journey together, take a second to subscribe to the channel. We are working toward our goal of 1,000 subscribers, and your support helps us bring you more stories that uncover the greatest mysteries of science, history, and the universe. Now, let's go back to where this extraordinary story truly began. Decades ago. In September 1977, Voyager 1 lifted off from Earth carrying 10 scientific instruments: cameras, plasma detectors, cosmic ray sensors, magnetometers, ultraviolet spectrometers, every one of them designed for a mission expected to last only 5 years. The plan was straightforward: visit Jupiter and Saturn, capture images, collect data, send everything back to Earth, and eventually fall silent. No one expected anything more. Certainly, no engineer standing on the launch pad imagined that nearly half a century later, another generation of scientists would still be communicating with the same spacecraft. Yet Voyager refused to stop. Year after year, it continued its lonely journey. It sailed beyond Neptune, crossed Pluto's orbit, left the Kuiper Belt behind, pushed through the termination shock, crossed the heliosheath, and finally reached the invisible frontier where the Sun's influence ends. In 2012, after years of careful analysis, NASA confirmed what many had hoped but few dared believe. Voyager 1 had crossed the heliopause. For the first time in history, a machine built by human hands had entered true interstellar space, the vast region between the stars where no spacecraft had ever traveled before. There was no celebration waiting for it. No applause echoed across the darkness. Voyager crossed the boundary completely alone, yet it kept talking. Even now, nearly 49 years after launch, the spacecraft continues sending tiny whispers back to Earth. Each transmission is like a heartbeat, measured not in pulses, but in radio waves that require almost 23 hours to complete their journey. Think about what that really means. When engineers at NASA's Jet Propulsion Laboratory send Voyager 1 a command today, they cannot know whether it worked until nearly 2 days later. Every conversation with the spacecraft unfolds across almost 46 hours. Every decision is separated by unimaginable distance, and those decisions have never mattered more. Back in 1977, Voyager's 3 radioisotope thermoelectric generators produced roughly 470 watts of electrical power, using the natural decay of plutonium-238. That may not sound like much. A household hairdryer uses even more electricity, but it was carefully managed to power every onboard system. The problem is that radioactive decay never stops. Every year, Voyager loses approximately 4 watts of power. The decline is slow, relentless, and mathematically unavoidable. By 2026, those generators produce only about 250 watts, barely half their original output. Yet, those remaining watts must heat fuel lines, operate navigation systems, power scientific instruments, maintain communication, and keep the spacecraft's antenna aimed precisely toward a tiny blue planet more than 15 billion miles away. There simply is not enough energy for everything. Something has to be sacrificed. And that is exactly what began happening. Inside JPL, engineers gathered around spreadsheets, simulations, and decades of engineering experience, knowing they faced impossible choices. Every instrument represented years of scientific discovery, decades of uninterrupted observations, and countless researchers who had built careers around its data. Yet keeping every instrument alive would eventually mean losing the spacecraft entirely. On February 25, 2025, they made their first painful decision. The cosmic ray subsystem, which had operated almost continuously since 1977, was switched off. For nearly 50 years, it had measured high-energy particles created by exploding stars and violent events across the galaxy. It helped scientists understand where our solar system ends and interstellar space begins. Nothing was wrong with it. It had not failed. It was simply too expensive to keep alive. The electricity was needed somewhere else. The command traveled through space for nearly 23 hours before reaching Voyager. Quietly, without ceremony, one of humanity's oldest scientific eyes closed forever. The engineers did not celebrate. The scientists whose careers had depended on its observations did not celebrate either. They simply accepted the sacrifice, documented its remarkable legacy, and continued searching for ways to keep the remaining instruments alive just a little longer. Because every extra month Voyager survives is another month. Humanity continues listening directly to the space between the stars. The first sacrifice had bought Voyager 1 a little more time. For a while, that was enough. Inside the control rooms at NASA's Jet Propulsion Laboratory, engineers knew exactly what they had purchased with that decision. They had not saved the spacecraft. They had simply delayed the next goodbye. That goodbye arrived sooner than anyone wanted. Less than 14 months after the cosmic ray subsystem fell silent, another difficult meeting ended with another unavoidable decision. On April 17, 2026, a single command began its 23-hour journey across interstellar space. Its destination was Voyager 1. Its purpose was to switch off the low-energy charged particles experiment, the LECP. For almost 49 years, the instrument had faithfully measured ions, electrons, and cosmic rays. It had been working since the day Voyager left Earth, quietly recording the invisible particles streaming through the solar system and beyond. There was nothing wrong with it. Like the instrument before it, the LECP had not failed. It simply needed more electricity than Voyager could spare. Nearly a full day after the command left Pasadena, California, it finally reached the spacecraft. Somewhere beyond the heliopause, in the silent darkness between the stars, another scientific instrument shut its eyes forever. No applause followed. The engineers who authorized the shutdown felt no triumph. The scientists whose careers had been built around decades of LECP data felt no satisfaction. Instead, they did what scientists have always done when something precious comes to an end. They documented its remarkable legacy, expressed their gratitude, and turned their attention toward keeping the mission alive for just a little longer. When the shutdown was complete, Voyager 1 had only 2 scientific instruments still operating. Just 2. Out of the 10 that had launched with it in 1977. It was as though a traveler who had once explored the universe with 10 fully open senses was now continuing the journey with only 2. Those last surviving senses were the magnetometer and the plasma wave subsystem. Neither could take photographs, neither could reveal breathtaking landscapes or colorful planets. Instead, they listened. The magnetometer quietly measured the invisible magnetic fields flowing through interstellar space. The plasma wave subsystem listened to subtle oscillations moving through plasma, the thin, electrically charged gas that fills the immense distances between stars. They were not glamorous instruments, yet they were performing something no other scientific equipment anywhere else could accomplish. They were taking direct measurements from inside interstellar space itself. Not from computer simulations, not from telescopes observing at a distance, but from a spacecraft that was actually there. Every new reading carried information about the temperature, the texture, and the magnetic heartbeat of the galaxy beyond our solar system. And every one of those discoveries depended on a power supply that became 4 watts weaker every year. It was one of the most delicate balancing acts in the history of space exploration. There was no safety net. Few people outside NASA ever realized how much pressure rested on the engineering team responsible for Voyager 1. Most of the people now operating the spacecraft had not even been born when it launched. They inherited a machine they never designed. They learned software written before personal computers became common. They communicated with a spacecraft through the enormous antennas of the Deep Space Network, while trying to manage a vehicle farther away than any human creation had ever traveled. Distance changed everything. If an engineer accidentally sent the wrong command, there was no immediate correction. Nearly 23 hours would pass before Voyager received the instruction. Only after another 23 hours would Earth learn whether the command had worked, or whether something had gone terribly wrong. Every conversation lasted 40. Every decision unfolded over days instead of minutes. And as Voyager's available power continued shrinking, every choice became more permanent than the last. Yet electricity was only part of the problem. The greater danger surrounded the spacecraft itself. Out in interstellar space, where temperatures approach -270 degrees Celsius, survival depends on staying warm enough to keep critical systems alive. Among the most vulnerable components were Voyager's hydrazine fuel lines. Those tiny tubes carried the propellant that allowed the spacecraft to adjust its orientation and keep its antenna aimed precisely at Earth. If those lines ever froze, Voyager would lose the ability to point toward home. Its antenna would slowly drift away. The radio signal would disappear, not gradually, not with warning. It would simply vanish. And once communication was lost, there would be no way to tell Voyager how to recover. The engineers at JPL understood this better than anyone. Every heater they turned off saved precious electricity, but every heater they turned off also brought the spacecraft closer to freezing. Every scientific instrument sacrificed extended the mission. Every sacrifice also increased the risk that the spacecraft itself might become too cold to survive. This was not a distant possibility. It was the reality they faced every single day. As difficult as those choices already were, an even greater milestone waited just ahead. In November 2026, Voyager 1 would reach a distance no human-made object had ever achieved before. Its radio signal would require a full 24 hours to travel one way. One light day. The phrase sounds almost poetic, as though it belongs in science fiction. For the engineers responsible for Voyager, however, it represented something far more serious. A single exchange between Earth and the spacecraft would now require 48 hours, 2 full days. Voyager would become more independent than anyone had ever intended. Out there in the darkness, it would continue operating according to software written during the 1970s, powered by generators that weakened every year, relying on only 2 surviving instruments to explore the vast magnetic fields and plasma that fill the space between the stars. And the people back on Earth could do little more than wait, hoping that 2 days later, Voyager would answer once again. For the people waiting on Earth, patience had become part of the mission. Every time a command left the Deep Space Network, there was nothing left to do but wait. Nearly 24 hours for Voyager 1 to receive it. Nearly another 24 hours before the answer returned. At best, humanity could check on its most distant explorer only once every 2 days. And yet, despite everything that had been sacrificed, despite the shrinking power supply and the growing silence, Voyager 1 was still alive. Not loudly, not dramatically, but unmistakably alive. Even now, as this story unfolds, a tiny radio signal is crossing more than 15 billion miles of interstellar darkness. Hidden inside that almost unimaginably weak transmission is data collected by Voyager's final 2 surviving instruments, the magnetometer and the plasma wave subsystem. More than that, the signal carries proof that the spacecraft itself is still alive. It is the heartbeat of a machine that was expected to survive only 5 years, yet somehow continues speaking nearly 49 years after leaving Earth. By the time that signal finally reaches our planet, it is unimaginably faint. Its power is weaker than the weakest Wi-Fi signal most people have ever experienced. Yet, the giant antennas of NASA's Deep Space Network patiently catch it. They amplify it. They decode it. And finally, they deliver it into the hands of scientists who, even after half a century, are still learning entirely new things from Voyager 1's lonely journey. The spacecraft has become old. Its discoveries have not. According to scientists studying its latest measurements, the plasma wave subsystem has revealed persistent density variations throughout the interstellar medium that existing theoretical models had never fully predicted. Even after losing most of its scientific instruments, Voyager 1 continues to surprise the people who built it. It is not merely surviving, it is still exploring. But while the public watches Voyager's slow decline, another story has been quietly unfolding behind the scenes. Inside JPL, engineers have been discussing a plan so ambitious that even they sometimes describe it as sounding like science fiction. Informally, they call it the Big Bang. The name has nothing to do with the birth of the universe. Instead, it refers to a bold new strategy for managing Voyager's remaining electrical power, an attempt to squeeze more life out of a spacecraft that has already exceeded every expectation anyone ever had for it. The engineers know the risks. That is why they intend to test the idea on Voyager 2 first. Voyager 2 still has slightly more available power and is somewhat closer to Earth, making it the safer spacecraft on which to attempt such an experiment. If the approach succeeds there, the team hopes to perform the same procedure on Voyager 1, no earlier than July 2026. And if everything works exactly as planned, something remarkable could happen. The low-energy charged particles experiment, the instrument that everyone believed had been lost forever when it was switched off in April, might actually come back to life. Imagine that for a moment. An instrument pronounced dead, returning to service nearly half a century after launch. It sounds almost impossible. But possibility is exactly what keeps the engineers working. They also know the other side of the equation. If the maneuver fails, if a single command sent across 23 hours of empty space produces an unexpected result, there will be no quick correction, no emergency response, no second attempt. The consequences could be permanent. Every decision now carries enormous weight because every mistake may be irreversible. That is the reality facing the people responsible for humanity's most distant explorer. Stepping back from the engineering challenges, however, reveals an even larger truth. Voyager 1 is the only spacecraft in history to enter interstellar space and remain alive long enough to tell us what it found there. Voyager 2 is the only other spacecraft sharing that extraordinary responsibility, following a different path through a different region of the interstellar medium. Together, they are humanity's only direct senses beyond the solar system. And one day, those senses will disappear. Eventually, the remaining instruments aboard both spacecraft will require more power than their aging generators can provide. Eventually, the final signals will fade beneath the threshold of detection. And when that happens, humanity will lose its only direct connection to the space between the stars. There is no Voyager 3 waiting on a launch pad. There is no successor already flying toward the heliopause. There is no replacement mission expected to reach that distant boundary within the lifetime of anyone alive today. Even if a new interstellar probe launched tomorrow using the best propulsion technology currently available, optimistic estimates suggest it would not arrive until sometime in the 2050s or perhaps even the 2060s. And even those estimates assume everything goes perfectly. That is why every new transmission from Voyager 1 matters. Every measurement, every radio signal, every additional month of operation. Because what Voyager 1 and Voyager 2 are doing today cannot be duplicated by anything else humanity possesses. Their mission is no longer simply historic. It has become irreplaceable. And while the engineers struggle to preserve those final measurements, another part of Voyager's mission continues quietly, untouched by failing instruments or dwindling electrical power. Long before the spacecraft ever reached interstellar space, the people who built it understood something extraordinary. They were not sending only a scientific probe into the universe, they were sending a message. Bolted to Voyager 1's side is a gold-plated copper disc known simply as the Golden Record. Inside it are 115 images showing Earth and its inhabitants. Greetings spoken in 55 human languages. The sounds of oceans, birds, thunder, laughter, machinery, and life itself. 90 minutes of music gathered from cultures across every continent. Etched onto its surface is a mathematical map using nearby pulsars to reveal the location of our solar system. It contains nothing less than the coordinates of home. Carl Sagan and the team who created the Golden Record never assumed another civilization would certainly find it. That was never the point. The point was the gesture itself. To reach into the unknown and simply say, "We are here. We exist. We are capable of beauty." Even if no one ever answered, even if no one ever listened, that message was worth sending. And now, in 2026, while Voyager 1 slowly falls silent one instrument at a time, that message continues its endless journey through the stars. Long after the scientific instruments have gone quiet, the Golden Record will keep traveling. The Golden Record continued its journey without asking for permission from time. Even now, it races through interstellar space at nearly 38,000 miles per hour, carrying humanity's portrait into a universe that has never answered. Inside that golden disk are our voices, our music, our languages, and the story of the tiny blue world that created it. Nothing about Voyager's fading power can change that. Long after the final radio transmission reaches Earth, long after the last engineer who ever worked on the Voyager program is gone, long after our civilization has changed into something future generations would barely recognize, the Golden Record will still be traveling. 40,000 years from now, Voyager 1 will make its closest approach to another star system, and the message humanity created back in 1977 will still be there, patiently waiting for someone or something to discover it. That thought raises a question few people ever stop to ask. What does it actually mean to be alive while this moment is happening? Not what historians will someday write. Not what textbooks will eventually say. But what it means for us, living right now, to witness the final chapter of perhaps the most extraordinary scientific journey humanity has ever attempted. There are people alive today who watched Voyager 1 leave Earth in 1977. Some were children standing in front of television screens. Others were engineers standing beside launch consoles. Some devoted their entire careers to this single spacecraft. They designed instruments that are now being switched off one by one. They spent decades studying signals arriving from beyond the solar system. They gave the best years of their professional lives to a machine that is now surviving on borrowed power and borrowed time. For them, Voyager is not simply a mission, it is the story of their lives. Yet even for people who have never paid much attention to space exploration, there is something strangely human about Voyager's slow fading. Every machine eventually reaches its end. Every signal grows weaker. Every voice, no matter how powerful, eventually becomes silence. But silence is not the same thing as disappearance. One day, Voyager 1's final scientific instrument will demand more electricity than its aging generators can provide. One day, the Deep Space Network will wait for a signal that never arrives. The heartbeat from interstellar space will finally stop, but Voyager itself will not. The spacecraft will continue moving. It will drift through the darkness between the stars at nearly 38,000 miles per hour. It will continue that journey for millions of years. The metals that form its body were forged inside ancient stars billions of years before Earth even existed. The copper inside the golden record was mined by human hands. The mathematics engraved onto its surface were discovered by minds that lived for only a tiny fraction of cosmic history.